afternoon. For this short talk, I'm going to illustrate how to use the automatically detect the prostate cancer using a multi-parametric MRI. Here is just a brief background. Today's prostate cancers count to like 20% of the new cancer cases among the men in the US. It's just about like a second next to the lung cancer. And based on the statistics of all the diagnostic cancers, the 5-year survival rate is about 98% for the prostate cancer patient. So that means if we have the effective screening and early diagnosis of prostate cancer, which probably should, it should be get a very successful treatment. So in that case, the MRI actually is getting more and more increasing use in the hospitals, and particularly for the multiple parametric MRI is currently is standard uses to the prostate cancer risk detections. But however, they still have up to 30% of the clinical misclassifications. So we aim at designing the, which is called the application programming interface, which can synchronize the MRI visualization and the image viewer all together, and to facilitate the cancer detection, coupled with the increasing the diagnosis accuracy improvement. Oh, sorry about that. I forgot to do this. Okay, here's the structure of the prostate cancer finder API. So the structure, which is based on the open source web-based platform called the Open Health Imaging Foundation, which can deploy the AI models and displays the image viewing and the reporting interface simultaneously. And the prostate cancer finder API consists of the image viewer interface and the model containing the deep learning basis and the DICOM medical images server, and to predict the prostate cancer. Then before we try to train the model, the most important thing is to collect the data. We got to get the data ready before training the model or construct the model. So the MR prostate images is performed on which is called it's a Rotterdam University in the Netherlands, and the data set consists of 346 patients. And 204 patients are in the training cohort, and 142 remaining patients in the test cohort. And they are, for each patient, they contains at least 4 different MRI images, all called modalities. So which is including the T2 weighted images, and the diffusion coefficient images, and diffusion weighted images, and the K-train map images. And then we get to randomly select the image patches, which is across all the 4 different image modalities, and coordinate all of them, put them together. And here is the model we are doing. So for each of the random selected image patches, we consider as an input of this convolutional neural network input, and in each of them will be fed into each of the branch of the convolutional network, and then all of them merge together with the fully connected layers. And before doing the prediction, we apply for the sigmoid function to do the prediction. And here shows the snapshot of the PCA cancer APIs. And it contains 6 different image panels to show the image modalities across 4 different MRI modalities, including the T2 weighted image, which is, let me see here, okay. Here is T2 weighted images, and here is the diffusion coefficient images, and this is called the coefficient weighted images, and this is the one actually we doing the image segmentation on the prostate on top of the T2 weighted images. And there's another one showing the prostate cancer heat map on top of the T2 weighted image. And this one is the K-train images. And because of the image contrast too high to see the details, but they will be easier to see, from the live demos, because we can adjust the image contrast levels. And here is actually when we click the location showing on the tag with the finding 8, this is the location we attempt to, or precisely, we should say the model was assigned to do the prediction. So within this, you'll see, okay, the outcome is the probability of the finding the significant. Indicates if the probability is higher, there's a good, the better confidence to find the cancer around this location. So beyond that, we're still working on the model improvement. We use a different approach by assembling the image stacks from 4 different MRI modalities into the 4D image stacks before doing the image patch selection. And then, in addition, we choose the DenseNet as the background, which is the one of the state-of-the-art CNN architecture. And we use this as a background architecture in addition to the this trainable loss function, which is named as the focal loss. And putting together, then we try to improve the model accuracies as well as the model stabilities. And once we get once it's well trained, we are putting it together into the API, and which will be done in a very near future. And thanks for your attention. Yeah. Thanks.